My name is Muhammad Asyraf bin BURHAN. I am from 2 BEEI S1 Stroke 1 for subject BEEA year 2020 and 2021. My question is part B, question 3. So for the first questions, question A, Mr. Faris Ezon implemented a PID controller to control his aerial drone. The drone produced a sinusoidal movement, a pattern on y-axis given a constant input. Assuming the drone's control system is a second order system, what is the damping ratio of the system? Why? So the answer for this question is the constant input can be treated as the input. As we know, the output is a sinusoidal pattern with no decay in amplitude. Hence, the system is undamped system. Undamped system gives the sinusoidal output for a step input. For an undamped system, damping ratio is 0. So the response will be sinusoidal signal with a DC value equal to the amplitude of the step input. Question B. The question asks figure Q3b shows the response of the underdamped second order system where T is time in second and T is the output response in meter. Determine the percentage overshoot, damping ratio, natural frequency, settling time, transfer function of the system, type of the input, the force response value, and the natural response value and stability of the system. And the last question is one application that associate with the output response. So we will go to the first question. The percentage overshoot. The formula for percentage overshoot is peak value minus final value over final value times 100%. So as we know, the peak value is 1.4 and the final value is 1. So we just transfer the data to the formula and we will get 40%. And the second one is damping ratio. Damping ratio formula we will get from the percentage overshoot, which is minus exponents times lambda times damping ratio over square root of 1 minus damping ratio square times 100%, which we get 40%. So we just transfer it and we substitute the other value and then make the damping ratio square as the main key, and the final answer we will get for damping ratio is 0.306. For number 3, natural frequency with given peak time is 4 seconds. So as we know, peak value, the formula is lambda over omega d. So the times given is 4 seconds. We substitute the 4 and 4 equals to lambda over omega d. Then we just substitute and do the mathematical procedure. We will get the final answer for natural frequency is 0.825 radian per second. The question 4 is about settling time. So settling time for second order under damp is Ts equals to 4 over damping ratio times natural frequency. So the value for these two below the equation is we got from earlier. We just substitute it back and we get settling time, which is we get 15.845 seconds. And for number 5 is transfer function of the system. So the transfer function we for second order under damp is like this: omega n square over s square plus 2 damping times damping ratio and natural frequency times n times s plus omega n square. So as we know, the damping ratio from the earlier is 0.306 and the natural frequency is 0.825 radian per second. So for omega n square, we just square the value of the natural frequency, so we get 0.681 radian per second. And for the last component is 2 times damping ratio and natural frequency. So we just substitute the value and we will get 0.5049. So with all the components, we just substitute the value for the formula, and hence that's the formula for transfer function of the system is S equals to 0.681 over S squared plus 0.549 S plus 0.681. And the next question is type of the input. The type of the input for this question is type signal UT. And for the next question, the force response value. Force response is this called is steady state response. So the formula is CT equals 1 minus exponent power of negative damping ratio times natural frequency and times over power root of 1 minus damping ratio square, and the whole need to times omega d t plus angle. So hence the force response value for this one is 1. The next question is the natural response value. Natural response value is equal to negative exponents in the power of negative 0.25 t sine in the bracket of lambda over 4 t plus 72.18. The stability of the system, we got the time setting is equal to 0.681 over S square plus 0.509 S plus 0.681. So we know that 0 equals to negative 0.681, and the poles is we got to negative 0.5049 J and negative 0.681 J. We just turn it into the negative value from the equation. So pole at the left sides are 2 and poles at the right side are 0, while the poles at the imaginary axis also 0. Hence the system is stable. And the last one is the application that associate with the output response. So the application that associate with the output response is a diving board. The questions asked about table Q3C shows the reading obtained by first order system with the unit step input where CT is the response while T is time. The given UT equals to 3. So the first question it asks about the sketch the output response of the system. So the answer will be like this, where the y-axis will be labeled as meter and the x-axis will be time. So the next question is determine the time constant. Time constant for the first order system, we can know that time constant is 63% from the final value. So 63% of the final value, we calculate it and we will get 2.5 seconds. And the next question is about rise time. So the rise time for the waveform to go from 10% to 90% of its final value. So the formula is TR equals to in the bracket of 3 times 90% minus in the bracket of 3 times 10%. So we will get 2.4 times 2.5 and the final answer will be 6 seconds. For the settling times we got TS equals to 4 in the bracket of T. So we just substitute the value of T with we got from the second question, which is 2.5. So 4 times 2.5 equals to 10 seconds. For the next question, output response in time domain. So output response is a CT equal to C infinity in the bracket of 1 minus exponent power of negative times over tau for T larger than 0. So we got CT equals to 2.99 in the bracket of 1 minus exponent in the power of negative T divided by 2.5. So hence we can assume the answer is CT is approximately to 3 in the bracket of 1 minus E in the power of negative T over 2.5. We just round off the 2.999 to 3. And the next question is force response value. So we just put t equals to infinity in the equation. So we got c infinity equals to 3 in the bracket of 1 minus exponent power infinity over negative 2.5, which we will get approximately almost to 3. So the final answer will be hence the first decimal value is approximately to 3. And the final question is about natural response value. So this is the transition part of the CT, which is become 0 if t equals to infinity. Hence the natural response value will be 3 exponent in power of negative 2.5 t. We get this answer from the from this equation. We just substitute times the 3 into the box with the exponent, and then we will get the natural response value. And that's all from me, and thank you.